So we're going to do a few more of these AIME II problems. I'm using slightly different tools this time from a different computer. I want to see how it works. So first read the question, be sure you understand it, and then I'll show you how I did it. So my picture's a little bit clunky, I'm sorry. I'm using drawing tools that I don't use very well, but I hope the idea is clear. It's the inner squares of length 15, the outer squares of length 40, and they're concentric. So in fact, there's 25 more units on the sides of the big square than there are on the little square, but because they're concentric, there's 12.5 on a top and 12.5 below and 12.5 to the left and 12.5 to the right. So what's important is that those isosceles triangles that you're going to fold up over the little square to make a pyramid all have altitude 12.5. So I hope you believe my horrible picture, but if you fold those sides up, you're going to get a pyramid whose base is a square of side length 15. And these triangular sides, it's the slant height that's 12.5. It's not the length of the sides of the faces of the triangular faces, and it's not the altitude of the pyramid. It's 12.5 is that slant height. And what I'd really like to get to find the volume of the pyramid is the altitude of the pyramid. So how do I do that? What you have to imagine is a cross section that goes through those two slant heights that are on opposite faces, as well as a length 15 from the base. And in fact, the altitude to that triangle is actually the altitude to the pyramid itself. Well, that's not so bad, because if you drop the altitude to that triangle, it bisects the base, because it's an isosceles triangle. So the side is 7.5. That's a nice right angle. And oh my gosh, it's a little bit disguised because of the halves, but if you think about it, that's 15. It's half of 15, and the hypotenuse is half of 25. This is a 3, 4, 5 triangle. Well, again, it's still a 3, 4, 5 triangle, but I was going to say that's 20, but in fact it's actually 10. It's half of 20. Because you could do the Pythagorean formula if you didn't remember it. You could take 12.5 squared minus 7.5 squared and take the square root, and it really is 100 when you work it all out. But I think if you recognize the 3, 4, 5 triangle, it saves you a lot of time. And we are so done, because the volume of a pyramid is 1/3 the area of the base times the height. That's a worthwhile formula to know, and in particular in this case it's 1/3. The area of the base is 15 squared times the height, which is 10, and you can multiply out if you want to, or you could say, gosh, 15 over 3 is 5, so it's 5 times 15 times 10, which is 750. And we're done. So here is question 6. And in question 6, we have, you might want to pause it and read it, or if you have it in your own copy, that's great. But we have complex numbers, and we're looking at all the complex numbers who have absolute value of 5, but we also want their imaginary part to be greater than 0. And then we're going to take the distance between 1 plus 2i times z cubed and z to the 5th. So let's see if we can figure out how to do that. So first of all, 1 plus 2i times z cubed minus z to the 5th, you can factor a z cubed out of that. And if you're taking the absolute value of these complex numbers, the absolute value of a product is still the product of absolute values. That hasn't changed. And in fact, that z cubed part, we're really done with already, because we know that if the absolute value of z equals 5, it's on the circle of radius 5 in the complex plane, about the origin. Well, then the absolute value of z cubed is going to be 125. So that part's the easy part. Maybe. But now we still have to figure out this 1 plus 2i minus z squared. So there's a couple of things to know here. And the first is the original numbers that we were looking at are all the numbers in the complex plane where the absolute value of z was 5. And they also wanted it was a plus bi where the b was greater than 0. So it's the part that I've highlighted on that circle. If that's the circle of radius 5 about the origin in the complex plane, then the highlighted part is the part that we want. But then now we're going to look at z squared. And z squared, now you need to know de Moivre's theorem about multiplying complex numbers. I don't think I'm going to go into it here. This is supposed to be a short lecture, but you might want to Google it if you're totally unfamiliar with it. I think if you didn't know anything about complex numbers and how they multiply and things like that, this would be a very hard problem to do. But if you're unfamiliar with it and you want to learn between now and next year's AIME, I think that's a very doable thing. So in any case, if you do know de Moivre's theorem, you know that when you multiply numbers who have absolute value 5, if you square such a number, the new number you're going to get is going to have absolute value 25, but also when you square it, it's going to be basically the angle that it makes with the x-axis is going to double. So whatever the original number, if the original number was over here, if you gave me a complex number somewhere on that circle of absolute value 5, and it happened to make some angle theta with the x-axis, then when you square it, you'll get a new number of norm 25, and I can't draw that to scale here, so I'm just going to draw a slightly larger concentric circle, and you'll have to pretend that it has norm 25, but what's important is that the square of that number will have an angle which is double the existing number. So the new number is on the circle of absolute value 25. Again, this is not the scale, I apologize for that, but it has double the angle the old one did, so that would be z squared. And now that means that if you look at the original numbers and you look at all possible ways to double their angle, you get all the numbers on the circle of radius 25. Because since the original ones have angles all the way from 0 to 180 degrees, when you square them, you'll get everything from 0 up to 360 degrees. So you go all the way around the circle. Every possible number on that circle is the square of something in our original domain. And all we're trying to do is find the one that when you take 1 plus 2i minus that number, you get the biggest possible value you can. But geometrically, that's just asking which point in that circle is farthest away from the point 1 plus 2i in the complex plane. And that's not so bad. You just take the diameter through 1 plus 2i, and you don't want the one over here is too close. In fact, it may be the closest point, and the one over here is the farthest point away. No point on the circle is farther away from 1 plus 2i than that. And so all we need to do is figure out what that length is. How far is this? Well, of course, we could actually find this point because we could use the slope of 1 plus 2i is slope 2, and you could go the other direction. We don't even need to do that. This is a circle of radius 25, so this part here is 25, and this length from the origin to 1 plus 2i has length square root of 5. So just as a vector, if we take 1 plus 2i and divide it by root 5 to get the unit vector in that direction and multiply it by negative 25, we want to go in the opposite direction and we want to go 25 units. Well, again, once we've divided by root 5 to normalize it, that would work. So that's the coordinates of this point down here, which is z squared. And the problem didn't even ask us for z, it asked us for z to the fourth. And so this is z squared. All I have to do is square this to get z to the fourth. And if I square it, I'm going to get, let's see, negative 25 squared is 625. Root 5 squared is 5. And then 1 plus 2i if you square it. Now I guess I will do the complex multiplication. It's going to be 1 squared plus 2 times 2i plus 2i squared, which of course 2i squared is negative 4, so it's 1 minus 4. It's going to be negative 3 plus 4i. And that whole thing, of course, times 625 over 5, which is 125. So it's negative 3 times 125 plus 4 times 125. And since the original, what we put on the answer sheet was, this is c plus di, so c is this thing and d is, 4 times 125 times I, d is this thing, then c plus d is just 1 times 125. So the answer to the actual question that was asked is 125. So in question 7, and again you should pause it and read it, we're looking at numbers that when you put them in binary they have 8 ones. And the smallest one is obviously 1, 1, 1, 1, 1, 1, 1, 1, and then the next one is going to be 1, 0, 1, 1, 1, 1, 1, 1, 1, and so forth. If you put them in order, we want to find the 1000th one. And I'm sure there's other ways to look at this, but it seemed to me like the easiest way to think about it is if I take 8 ones and some number of zeros, k zeros, then I have 8 plus k. Choose k. I hope we know what that means. That's this combinatorial idea. It's short for 8 plus k factorial divided by k factorial times 8 factorial. But it also stands for the number of ways, if you give me 8 plus k things, that I can pick k of them. In particular, if you give me 8 plus k positions for the digits, I can pick k of them to be zeros, or I can pick 8 of them if you want. It's the same deal, to be the ones. And so this is the number that counts. That includes leading zeros, but that's okay. This tells me that there's 8 plus k choose k, or many ways to choose numbers of at most 8 plus k digits that have 8 ones. That is, if the first few digits are zeros, some people say, well, that's not really a 8 plus k digit number. If I had 0, 0, 1, 1, 1, and 8 ones, that's really just an 8-digit number. Is that 8 ones? Yeah. But that's okay. What I'm really saying is, as long as I only use up to 10 digits, all the numbers that are 10 digits or smaller, this is how many ways there are to pick 8 of them to be ones and the other k of them to be zeros. Well, what's cool about that is I can compute those things pretty easily. So for example, there's there is exact 8 choose 8 is 1. There's only one way to do it with no zeros. That's also 8 choose 0, of course. 9 choose 8, which is the same as 9 choose 1, is 9. There are 9 numbers that have at most 1 0. And that's pretty clear, right? Because if the 0 was in front, that's really just the 8-digit one. I already wrote that. But then I also have all the other ones. I'm not going to write them all down. There's 8 more of these. I mean, there's 9 of them in all, because you really got, essentially you have 9 places where the 0 could be. Well, it keeps going like this. You could 10 choose 8 is how many numbers there are like this that have at most 10 digits. So 2 zeros, it's the same as 10 choose 2. And you should know that that's 10 times 9 over 2. That's 45. 11 choose 8, which is also 11 choose 3. I don't know why I'm writing it both ways. Is 11 times 10 times 9 over 6, which is, let's see, that's the same as 11 times 5 times 3. That's 165. So there's still, we're going to have to keep going. If we want to get to the 1,000th one, we're going to need more than 11-digit numbers. We're going to need maybe 12-digit numbers. Well, 12 choose 8 is 12 times 11 times 10 times 9 divided by 24. Oh, that's nice because these cancel with just a 2. And so I wind up with 11 times 5 times 9. That's 495. It's 3 times bigger than 165. So finally, 13 choose 8. Well, it's 13 times 12 times 11 times 10 times 9 divided by 5 factorial, which is 120. Oh, 120 is 12 times 10. So this is really just 13 times 11 times 9. And I don't know what that is off the top of my head, but I can tell you one thing. It's bigger than 1,000. So now we know it. 12 digits is not enough, but once we get to 13 digits, we are going to find this thing. So right off the bat, this number is going to be a 13-digit number, and in fact, it's going to start with a 1. I don't know what else is going to happen, but because the 12-digit numbers weren't, if it started with a 0, then it really was a 12-digit number, and I would have found it already. So I had to go to the 13th digit, so it really has to be a 1, and now there's going to be 12 more digits, 7 ones, and 5 zeros. So let me actually recap this a little bit. We know that there's 495 numbers that have 12 digits or fewer, always with 8 ones. And then there's this number that's bigger than 1,000 that have 13 choose 8, which is all the numbers that have 13 or fewer digits. So number 496 will be the first number with 13 digits. So it's going to be a 1 followed by 7 ones and 5 zeros. And that's going to be number 496. Right? The 495 numbers with 12 digits or fewer, this is the first number that has 13 digits. And I know, in fact, what that smallest number is. It's 1 followed by all the zeros, all 5 zeros, and then the 7 remaining ones. So that's not the answer to the question. I want number 1,000. But at least we're getting closer. So the natural question is, let's start looking at those numbers. We know the number is going to start with a 1 because by the time we reach 14-digit numbers, we've got to more than 1,000 numbers. So it's going to start with a 1. So does it start 1 0 or does it start 1 1? So let's count how many numbers start with a 1 0, and then after that you've got 7 ones and 4 zeros. That's what's left. And I had to rearrange. That's not hard to do because now there's 11 digits, the 7 ones and 4 zeros, and you can pick which of the 11 places the 4 zeros go. It's 11 choose 4. It's also 11 choose 7. 11 times 10 times 9 times 8 divided by 4 factorial, 24. Factor out the 8, the 9, you can cancel out a power of 3, and so you're 11 times 10 times 3. There's 330 of those. So that means there are 330 of those. There are 495 12-digit or fewer. So 495 plus 330 is 800 and something, 825, I guess. And so number 826 is going to be the first number bigger than that. So it's going to start with a 1 and a 1. And then we're going to have what's left. We still have 6 ones. And we still have all 5 zeros. Well, the smallest one, number 826, is the one that starts 1 1 and then 5 zeros, and the remaining 6 ones. But of course, we're going to keep going with this. Maybe the number now starts 1 1 0, or does it start 1 1 1? So the natural question is, if you start with 1 1 0, you've got 10 digits left. 6 of them are 1s and 4 of them are zeros. How many different numbers are there like that? 10 choose 6 or 10 choose 4. Either way, that's 10 times 9 times 8 times 7, all divided by 24. Well, again, the 8 cancels in a 3, so it's 10 times 3 times 7, which is 210. Ooh, I think we actually went a little bit over. So we're
the highest number of this form, so 110 and then 6 more ones followed by 4 more zeros, that number would be number 1035. We got to go 35 back. We could go either way. We could go back to number 826 and now add the 0 and see if we can add another 0, or we can start with this number 110 and the biggest number 1, put a 1 there and see how many go back. Both methods work. There's potential. The second one might be a little bit shorter, but there's also a little trick to it. So I'm going to do the second one, but you should be able to keep going this way. So just to point this out, that is, you really have two options. You can start from number 826, which was the smallest number that had 110, and then you can go up from there. So you're going to start with a 0 and say how many numbers start with a 0 and so forth. Or you can start with number 1035, which is the biggest number that starts 110, and work backwards. Say, well, how many numbers are 1101 and then stuff, and then subtract away from 1035. I'm inclined to do the second one just because it seems like we're closer. But there is a little bit of subtlety to this, so we're going to have to be a little careful if we do it this way. We could just keep going the way we were going, and it's fine. But I'm going to start from the top and work down. So the question is, how many numbers begin 1101 and then have 5 more ones and 4 more zeros? And we know the biggest one of those is number 1035. Well, of course, this is just 9 choose 4 or 9 choose 5. So it's 9 times 8 times 7 times 6 divided by 24. The 6 goes away, and the 8 you divide by 4 and you're left with 2. So it's 9 times 7 times 2. I don't know what that is. Well, I mean, it's 63 times 2. It's 126. I do know what that is. But it's certainly bigger than 35. So if the biggest one is 1035 and I take all of these away, I'd be too small. So I don't want to take all of them away. But now the next question is, what if I start with a 1? That is, let's look at all the numbers that start 11011. And again, the biggest one is number 1035 in our list. So this is going to be 8 choose 4, which is 8 times 7 times 6 times 5, all divided by 24. And once again, this is going to be 35 times 2. Ooh, we're getting close. 35 times 2, which is 70. And so now let's try one more. We'll start 110111, and now we'll have 3 ones and 4 zeros. Well, that's 7 choose 4, or 7 choose 3. I keep saying that. It's 7 times 6 times 5 over 6, or 7 times 6 times 5 times 4 over 24, either way. And that's 35. Ooh, and we're on number 135. So let's think about this. We're just about there, but we've got to be very careful. So the smallest one of these is actually number 1001, right? Because to go from 1001 to 1035, including both of them, that would be 35 elements. So that smallest one, number 1001, is 110111, and then all 4 zeros and then the 3 ones at the end. Of course, we want number 1000, so we actually want the biggest one that starts not 110111, but 110110. So we want the biggest one that starts 110110. And of course, then we still got 4 ones and 3 zeros left, and all the ones come first. So the number we seek is 110, 110, 1111, and there are still 3 zeros left. That's it. That's the number that we're after in binary. Of course, what we really asked for, remember what the question asked for, we want the remainder when this number is divided by 1,000. So first of all, let's turn this number, let's figure out what it is. Those are powers of 2. Think that's right. Remember, the rightmost digit is, this is the 0th position, right? 2 to the 0th. It's the constant line. So this is 2 to the 1st, 2nd, 3rd, 4th, 5th, and 6th. That's these guys. Not the 7th, but the 8th and the 9th, and then not the 10th, but the 11th and the 12th. Okay, great. We need to add this up. We just need the remainder when you divide by 1,000. So you should probably know your powers of 2. It definitely helps. 2,048. Oh, that's 1,024 is 2 to the 10th. So actually 2 to the 12th is 4,096. And right, so that plus 2,048, not 1,024, but yes to 512. And yes to 256, oops, not 265, but 256. And not 128, but yes to 64, 32, 16, and 8. So if we add these up, then again, I don't need the thousands place. I just need, because we're going to divide by 1,000 and take the remainder anyway. So I just need that part. And it's, I don't like it, but it's not that bad. I'll do it in groups here, right? 64 plus 32 is 96. 16 and 8 is 24. 256 and 512 is 768. And then the 48 and 96, forget the 4,000 and the 2,000, is 144. Okay, and 96 plus 24 is 120. 768 and 144, 12, 1, 912. And when I add these up, I get 1,032. But of course, I just care about the 032 when you divide it by 1,000. So the answer to the question is really 32.